Hello and welcome to this video. In this video, we will continue looking at the methods of vector data structure. In the last video, we had covered till reserve and we'll resume from reserve. So it might take quite a few videos because the documentation is quite big. So in any case, we will slowly go through this and eventually it will come to an end. So we start with the reserve. Reserves capacity for at least additional more elements to be inserted in the given T. The collection may reserve more space to speculatively avoid frequent reallocations. After calling reserve, capacity will be greater than or equal to self.len plus additional. Does nothing if capacity is already sufficient, and it panics if the new capacity exceeds max bytes. So suppose we create a vector of one element and we reserve 10, then the capacity will be greater than or equal to 11. Then we have reserve exact, and it reserves the minimum capacity for at least additional more elements to be inserted in the given T. Unlike reserve, this will not deliberately overallocate to speculatively avoid frequent allocations. After calling reserve exact, capacity will be greater than or equal to self.len plus additional. Does nothing if the capacity is already sufficient. Note that the allocator may give the collection more space than it requests. Therefore, capacity cannot be relied upon to be precisely minimal. Prefer reserve if future insertions are expected. And the panic condition is the same, so you reserve exact 10 and the capacity will be greater than or equal to 11. Now the next function is try reserve. It returns the result with unit return type and try reserve error. So there is an additional return element here. Tries to reserve capacity for at least additional more elements to be inserted in the given directory. The collection may reserve more space to speculatively avoid frequent relocations. After calling try reserve, capacity will be greater than or equal to self-len plus additional if it returns okay. Does nothing if capacity is already sufficient. This method preserves the contents even if an error occurs. If the capacity overflows or the allocator reports a failure, then an error is returned. So here we have processed data and it takes an argument, a vector by reference of type 32 returns a vector of type 32 or try reserve error. So it creates an output vector and it tries to reserve data and process data.len as the additional argument, and it extends the data. Okay, we know this rank in the middle of a complex word, and it multiplies each element by 2 and adds by 5 and finally returns okay. So if this fails, try reserve, it will then give try reserve error. Then we have try reserve exact. It is similar to reserve and reserve exact. So try reserve exact is the equivalent of try reserve exact. Similar stuff, I think, to nothing extra. Then we have shrink to fit. So shrinks the capacity of vector as much as possible. The behavior of this method depends on the allocator, which may either shrink the vector in place or reallocate. The resulting vector might still have some excess capacity, just as is the case for with capacity. The allocator shrink for more details. So we're not going to look at the allocator right now. So we have a vector with capacity 10. We insert 3, and then we call shrink to fit, and the capacity will be greater than or equal to 3. Then we have shrink to, which takes some capacity as an argument, shrinks the capacity of the vector with a lower bound. The capacity will remain at least as large as both the length and the supplied value. If the current capacity is less than lower limit, this is a no op. So we create a vector with capacity 10, insert 3 elements, capacity is greater than equal to 10. Then we shrink to 4, capacity will be greater than equal to 4, shrink to 0. Then capacity will be greater than equal to 3 because here it will be a no op. Okay, current capacity is basically current capacity is less than lower limit. Okay, here current capacity is more than the lower limit which is specified. Then trashing to fit nightly APIs. Okay, into box slice converts the vector into a box T. Before doing the conversion, this method discards excess capacity like shrink to fit. So we have vector and you take a slice, make it a slice, p dot into box slice. Any excess memory is removed. So we have with capacity, we create element with 3, vector with 3 elements, capacity will be greater than equal to 10. Then we take the slice and we then convert that slice into vec, which will convert the box of this type into a vector and capacity will be 3. Then we have truncate, shortens the vector keeping the first len elements and dropping the rest. It takes an argument len. If len is greater or equal to the vector's current length, this has no effect. The drain method can emulate trunc but causes the excess elements to be returned instead of dropped. Note that this method has no effect on allocated capacity of the vector. So truncating the 5 element vector to 2, we create a vector with element 5, then truncate to 2, and new vector will be 1, 2. Note truncation occurs when len is greater than the vector's current length. So we have 3 elements and truncate is 8. So we have 3 elements remaining. Truncating len is equal to 0 is equivalent to following the clear method. So 1, 2, 3 is there. We truncate with 0, we get an empty vector. Then we have a slice. We extract the slice containing the entire vector. So we have the vector and we take it as a slice. Okay. And IO will probably print it into some sort of buffer. Okay. It goes to sync actually. Then we have as mutable slice, similar to slice, but it will be mutable now. Okay. So you can actually try to run this. Oh, I don't have internet connection, I forgot. You see this airplane mode, I'm not right now connected to internet. Then we have as PTR, which returns a raw const PTR, returns a raw pointer to the vector's buffer or a dangling raw pointer valid for 0 size reads if the vector did not allocate. The caller must ensure that the vector outlays the pointer which function returns, or else it will end up dangling. Modifying the vector may cause its buffer to be reallocated, which would also make any pointers to it invalid. The caller must also ensure that the memory the pointer points to is never returned to except inside an unsafe cell. Using this pointer or any pointer derived from it, you need to mutate the contents of the slice used as mutptr. This method guarantees that for the purpose of the aliasing model, this method does not materialize a reference to the underlying slice, and thus the return pointer will remain valid when mixed with other calls to as PTR, as mutptr, and as non-null. Note that calling other methods that materialize mutable references to the slice or mutable references to specific events we are planning on accessing through this pointer, as well as writing to those elements, may still invalidate this pointer. See the second example below for how this guarantee can be used. So we have a vector 1 to 4, we convert it into const PTR, and then the unsafe block, we iterate over the PTR, okay? And what we do is we dereference the pointer and we add I, and 1 is shifted I times. Okay? Due to aliasing guarantees, the following code is illegal. Sorry. So vector 0, 1, 2 is there, we take as a pointer, we read the pointer and discard it. Then we take PTR2, we as mid PTR and offset 2, and we write over value 2. Notably, the write to PTR2 did not invalidate PTR1 because it mutated a different element. And then we can again read PTR and discard it. Now we have S PTR, so similar stuff, but now it is mutable. So the important section is this one. This method also guarantees as long as key is non-zero side and the capacity is non-zero, the pointer may be passed into DLOC with a layout of layout colon array colon T capacity. In order to deallocate the backing memory, if this is done, be careful not to run the destructor of the vet, as dropping it will result in double fills. Dropping the vet in a manually drop is very typical way to achieve this. So we have created a vector, we have taken as net PTR, then we iterate for the size. So size is 4, and then we call the add method and supply it I, and we have this I as a sign, and then we set the length as equal to size. And then what we do is we dereference the immutable PTR, and it will be equal to 0, 1, 2, 3. Okay. So due to aliasing guarantees, following code is illegal. So similar stuff like PTR. Now we see the manually drop. Deallocating a vector using box which uses DLOC internally. So we construct an object manually drop. We have a vector 0, 1, 2. We take as mutable PTR and capacity is the capacity of vector. Then we take a slice of from raw parts mutable PTR. I believe this is nightly API. So okay, so we take the slice and we drop it in an unsafe block from raw. As non-null is nightly, allocated nightly, we have set length which sets the length. Forces the length of the vector to new length, takes an argument new length. This is a low-level operation that maintains none of the normal invariants of the type. Normally, changing the length of the vector is done using one of the safe operations in script such as truncate, decide, extend, or clear. New length must be less than or equal to capacity. The elements at old length new length, that is between this slice, must be initialized. C spare capacity method, for example, with safe initialization of capacity elements and use of this method. Setlen can be useful for situation in which the vector is serving as a buffer for other code, particularly over FFI. So we are going to get a dictionary which returns an option of vector of type UI. So we create a vector with capacity of 32 KB and dictionary length is 0. Then in unsafe call, okay, this will be, let's see what is going on. Okay, in unsafe call with deflate get dictionary call is there. Okay, so I don't know where this call is coming from. In any case, we will assume that it gets some dictionary which is a vector, and if r is equal to z, okay, then dict dot set length is equal to dict length. So this deflate get dictionary, it receives our dictionary vector as a mutable pointer, and the dictionary length is also received, that is 0. And I don't know about this. This self.strm is part of something else. So once we have this, we return the dict, and if there is a problem in deflating get dictionary, we return none. So this is an FFI call. So what this means is it is most probably a C function, okay, or C++ function. I don't know. While the following example is sound, there is a memory leak since the inner vectors were not freed prior to the Setlen call. So we have a vector which consists of 3 vectors, each of 3 elements, and we set the length to 0. So unsafe operations usually you should not do. Okay. There is no reason to call set length 0. You can clear this vector as well. Then we have swap remove, which takes an index and returns an element t. Removes an element from the vector and returns it. The removed element is replaced by the last element of the vector. This does not preserve ordering of the remaining elements, but is O1. If you need to preserve the element order, use remove instead. Panics if index is out of bounds. So we have 4 elements. We swap 1, swap remove 1. So it will return our first element bar and it will be set by QUX. So now the new vector is full QX bars. And we will do now the swap remove full. So bars will come at the beginning. Then we have insert function at an index, it takes an index argument as well as element. Inserts an element at position index within the vector, shifting all elements after it to the right. So it is an ON operation. So it takes O vector length time. All items after the insertion index must be shifted to the right. In the worst case, all elements are shifted, then the insertion index is 0. Then we have insert mutable. It takes an index, an element, and returns a mutable element. Insert an element at position index using the vector, shifting all elements to the right, and returning a reference to the new element. So the difference is that insert does not return anything, but insert mutable will return a reference to the element inserted. Then we have remove, takes an index, returns the removed element. Removes and returns the element at position index within the vector, shifting all elements after it to the left. Because this shifts over the remaining elements, it has a worst case performance of ON. If you don't need the order of elements to be preserved, you will swap remove instead. If you like to remove elements from the beginning of the vec, consider using vec dequeue pop front instead. And it also panics if index is out of bounds. Next, we have try remove, which is nightly, we don't care, retain. Retain is basically it's a function or it's a closure actually of type F. Okay. So it is a mutable closure and takes a reference of the vector. Okay. So retains only the elements provided by the predicate. In other words, removes all elements E for which ampersand E returns false. This method operates in place, visiting each element exactly once in the original order and preserve the orders of the returned element. So suppose we have vector 1, 2, 3, 4, and our closure code is that it should be even. So if it is odd, it will be dropped. If it is even, it will be retained. And then we have vector 1, 2, 3, 5. We want to keep true. And true, right? So 2, 3, and 5 will be retained, 1 and 4 will be dropped. So here we create an iterator out of keep, and we call vector retain, and we iterate over this iterator, and we go on till it is not finished, and then our vector will retain elements 2, 3, and 5. Then we have retained it. Similar thing. So the difference is that this time it will take a mutable, closure, fnmut type. Okay. So we have return mut now, and it retains the elements same thing. In other words, removes all elements E set that ampersand mut returns false. So similar to that, and now we have closure code. So in this case, if the element, it is dereferenced because X is taken by reference, is less than equal to 3, that is 1 to 3, then it is added, 1 is added, so it becomes 2, 3, 4. And if it is greater than 3, then it will be dropped because we return false. So we have 2, 3, 4. So these are quite useful, retain and retain mut. Okay. You can pass a closure such that your operation always returns true and perform any kind of operation on the array or vector rather. Okay. So I think I will stop here. There is a lot of code to go through. So we will see the rest of the functions in the next video. We will start by dedupe by key. Okay. So it will take a while. Okay, going through standard library is never a joke, particularly if you want to cover everything. So I hope that you're enjoying this video and finding it useful for your study of Rust programming language. Rust is simply a fantastic programming language. Okay, there is no doubt about it. And I should, if I'm talking about myself, that I spend every day effort on learning this language more and more. Okay, there are quite a few books I still have to cover, and those are kind of advanced level books on Rust. For example, Rust Namicon, I have to still read the which deals with the unsafe Rust. Okay. And by the way, I have a question answer website. Of course, we won't be able to see it. So it is kundika.astrology.org. Okay. So you can come here and ask questions related to Rust programming language because YouTube content is not really good for code. So if your question involves code, you can come at kunjika.astrology.org. I have shown it in other videos also. In the next video, I will give you the link because I don't have internet connectivity right now. So you can come to kunjika.astrology.org or let me type the spelling for you. It is kunjika.astrology.org. You come here and ask your questions. You need a login. You can make a login and ask your questions. So thanks a lot for watching the video and keep learning. I'll see you in the next one. Till then, enjoy and sayonara.